So the one thing we're sure about angular momentum is that the generators obey these commutation relations. So we got these commutation relations by considering the properties of rotations. And note that different components of angular momentum don't commute with each other. That means we call the rotations a non-abelian group. An abelian group is a group where all the commutators of the generators are zero. For example, momenta. So all the different components of momentum commute with each other. So in other words, p in the x direction commutes with p in the y direction. And so these form an abelian group. So if all the generators of a group commute and it's an abelian group, then it doesn't matter what order you apply the generators. And it also doesn't matter what order you apply the actual transformations. So supposing we have the translations, remember the translations are generated by the momentum operator. So if the momentum operators commute, which they do, then translations should commute. So if I translate along this way and then up, I should get exactly the same things if I translate up and then along this way. And I do. Rotations do not commute. So supposing I'm going to rotate around that axis, and then I'm going to rotate around that axis. So if I rotate like that, and then like that, I get that orientation. But if I rotate that way first, and then like that, I get a completely different orientation. So you can see that the rotations don't commute. So we shouldn't expect the angular momentum to commute as well. You might wonder why we're taking such an abstract view of angular momentum, when classically we knew exactly what it was. It was just a vector that was r cross p. And we could possibly imagine a quantum version of that where we put hats on things. You might worry that r and p don't necessarily commute. We have the commutation relations. So it certainly matters what order we put, say, the y operator and the yth component of the momentum, because then we'll have a commutation between them. But if we have the cross product, then we always have different components of the position and the momentum operators, and you can see that they do in fact commute. So this is always safe. In component form, we can just write, where again we're using the Einstein summation notation, and we can therefore have a go at showing that the angular momentum that we've sort of invented here does in fact obey these commutation relations. I'd just like to really emphasize a key point here, which is when I substituted in the L in these two places, I was very careful to make sure that I got my dummy indices right and my free indices. So the free index is this first one, so I and I, so K has to be K and L has to be L. And then when I'm summing over these indices, I have to invent new things. So I can't use my J and K because I've already got my K there, so I use different ones. And over here, I had to use different ones again. I can guarantee that a lot of people will lose a lot of marks in the exam by not dealing with their indices correctly. Now, the commutator is linear, and we can expand out commutators like this using the formula that we've used many times now. We can apply it again, and when we apply it again, we can ignore terms that have R and R, although I'll write them out explicitly this time. Where I was very careful about the ordering. And as I discussed, those commutations are zero and those commutations are zero because the momenta commute with each other and position coordinates commute with each other. And we know exactly what these are. Where I was careful to include the minus sign when I had the commutator of P and R instead of R and P. Now we can simplify this a little bit by using the summation over the delta functions. Now we have lots of different uses of dummy variables here. I want to pull out the R and the P, so I'm going to change dummy variables so that in this case M goes to alpha and Q goes to beta. In this case we'll have P going to alpha and N going to beta. Okay, now to simplify that, I'm going to have to use an identity on the Levi-Civita tensor, which I'll write over here. And this is going to let me simplify this, but I'm going to have to get my index that I'm summing over to be the first one. So here I'm summing over P, which is the second and third index, and here I'm summing over Q, which is the third and second index. So I can swap these indices, I just get a minus sign each time. So if I swap the P and the K, I'll get a minus sign. And then if I swap this P and the L, I'll get a minus sign. Two minus signs cancel out. And then same over here, except I'm summing over the Q. And now I note that I've got a delta KL, delta alpha beta, so those two terms actually cancel, because I've got a minus and a plus. And so I've just got these two terms. And these two terms, if I remember that the delta function is symmetric with respect to its indices, I can just write in this form up here. And again, we can rearrange these indices. If I swap k and the w and then the w and the l, then I can get that, and I get two minus signs, which gives me nothing else. This here is exactly the w component of the orbital angular momentum. And so I have shown my commutation relations, that the commutation of Lk and Ll is exactly of this form, which shows that our orbital angular momentum, as defined here, as we invented, is indeed a valid type of angular momentum. So L is the generator of rotations for a particular Hilbert space. It's the generator of rotations for a wave function with a single component. And so, for example, you discussed it when you were looking at a particle in a central potential. Because the central potential has no angular dependence, then in fact the Hamiltonian was symmetric with respect to rotations, and that means that all the eigenstates of a particle in central potential are also eigenstates of this L. Specifically, they're eigenstates of both the L squared operator and, say, the Lz operator. And L can go from 0 all the way up to infinity. It can be any integer. And M is constrained to be between minus L and L in steps of 1.